So now we are done discussing about the interface flux in heat transfer and mass transfer. Now, the basic objective of studying transport phenomena is to correlate the heat transfer, mass transfer, and momentum transfer. Now that our video is concerned about heat transfer and mass transfer, so we will study how they are similar to each other. For that, we will analyze it over some mathematical equations which we derived in the previous video.
Hmm.
The first comparison between heat transfer and mass transfer is we can see the rate. So as discussed in the introduction video, we said that the rate is the only term which remains constant as it is irrespective of the changing area. So these are the formulas which we derived earlier. The first thing is rate of heat transfer is equal to AH into average heat transfer coefficient into characteristic temperature difference. And the rate of mass transfer is mass transfer area into local mass transfer coefficient into characteristic concentration difference. Now, these are both the rate equations. So,
Now we can
if
draw quite a similarity between these two equations because the equations are of rate. We can see both the terms of area. The next term, which is the transfer coefficient, it is average. So average transfer coefficient is there. And the third term is the characteristic driving force, we can say. So in term, for the case of heat transfer, it is temperature. In the case of mass transfer, it is concentration. So characteristics concentration difference and characteristic temperature difference. These are, so we can draw, we can see a similar pattern in the formula. Yeah.
even in the calculation of average transfer coefficient, both the transfer coefficient are calculated in the same manner, which is your local transfer coefficient into area divided by the total area, both mass transfer coefficient and heat transfer coefficient. So we can say that this generalized formula is common for both heat transfer and mass transfer. Now we will move on to the second comparison. So here, for heat transfer, the quantity by volume term at interface was practically impossible to determine. So we came up with the substitution of Newton's law of cooling, which states that the heat flux is equal to heat transfer coefficient into difference of temperature at the wall minus temperature of the bulk fluid, which is
Bulk.
flowing over the flat plate. This is commonly called as Newton's law of cooling. Similarly, when the concentration at interface is difficult to determine, so we came up with the replacement of the Slattery equation, which is the molar flux is equal to Kc, which is your mass transfer coefficient, into concentration at wall minus bulk concentration.
Here also we can see the similarity. There is similarity because in both the cases, we are unable to define the complex nature of flow characteristics. Therefore, we require an assumption, or we don't require an assumption, we require something which is apart from analytically proved, because we don't have any analytical solution to the differential term. That's why we want some equation, and we get that equation by experimentally uh, getting some data and then concluding. In both the cases, there is experimental equation. First is Newton law of cooling, which is experimentally derived. And in case of mass transfer, it is Slattery equation. It is also experimentally derived. And the format of the formula is also similar to each other.
Another fun fact is this law is also called as Newton law of heat transfer, and this latter equation is called as Newton law of mass transfer. So basically, the Newton law is also a similarity between heat transfer and mass transfer. Now, the next comparison is which we saw in the physical significance of transfer coefficients.
Yeah. So here we can see the temperature profile for heat transfer and the concentration profile for mass transfer. As discussed while our derivation, both of these distribution curves actually, uh, it has two curves actually. First is the actual curve, and a straight line is also there in both the cases. That is the ideal case. Now, where is the ideal case coming from? We are actually deriving it from the film theory. That is the two film theory. In both the cases, we assume there is a film of thickness delta T for heat transfer and delta C for mass transfer. We are assuming there is a thickness between the interface. It will have some resistance. That resistance can be used for the physical significance of transfer coefficient. So here we can see the relation between uh, thermal conductivity and heat transfer coefficient. And in case of mass transfer, we can see the relation between diffusivity and mass transfer coefficient. Both of them have the ratio, both of them have the ratio of the thickness of the stagnant film. And here also we can see the similarity.
Both these equations are derived by equating the basic two laws. Like for heat transfer, it was the Fourier's law and the Newton law of